Welcome to part 3 of the lab. In this part, we're going to be designing a voltage regulator that uses a Zener diode to give us a steady 5 volts output. We're going to be choosing a value for RS. We're going to be choosing power ratings for RS and the Zener diode. And we're going to be doing 2 tests on it, a line test and a load test. A line test is a measure of, as this varies from 8 to 14 volts, how steady does our 5 volts stay? And a load test is, as we change this current here, how steady does our 5 volt there as well? They're both good measures of the quality of a DC power supply. So a line test is going to be a graph that looks like this. This is going to be V out on this axis. There's 5. And this is going to be V sub S on this axis. And what we're going to see as Vs rates from 8 to 14 volts, that we'd like to see that this holds pretty steady. Now, what we are going to see is that there is a little bit of a slope to that. There's a little bit of a rise to that because it's not a perfect regulator. And so we're going to try to measure that slope. The closer that slope gets to 0, the more perfect the regulator is. So, but we're going to take a measurement of this slope just by taking this point and that point, changing Y, changing X, get the slope. Okay, so this is what we're going to do for a line test. And then what we're going to do for a load test is we're going to set our Vs in the middle of the range, let's say 11 volts. And then we're going to have a graph of V out once again, but in this case versus I out. And what we're going to see is that for very light loading, V out is going to stay pretty constant. But then as the loading gets heavier and heavier, it's going to drop off. So we're going to use this variable output current by dialing up different resistors here on a decade box. A decade box is just a box with a whole bunch of resistors in it. You just dial up a value and it gives them to you. And we're going to do a series of measurements versus V out versus I out. And we're going to see how much current can this tolerate before it starts to lose the 5 volts. So that is a load test. We're going to be doing those 2 tests. So before we do that, let's do some quick calculations. We'd like to first find R sub S, our series resistor. R sub S is going to be V S min minus V out over I ZD min plus I load. So that's an equation that we gave you in class. Plugging in numbers here, we're going to be 8 volts minus 5 volts divided by, we're going to assume a minimum current through the Zener diode of 5 milliamps, but we will check that on the curve tracer to make sure that it is in its Zener region at 5 milliamps of reverse current. And then I load current, we're going to get by just good old Ohm's law. 5 volts divided by 500 ohms is 10 milliamps. So the 10 milliamps again is just Ohm's law current through this resistor here. 5 volts divided by 500 ohms is 10 milliamps. And when we plug in all those numbers, we're going to get 200 ohms. Okay. And now to get the power of that resistor, power in the resistor is equal to I squared R equals worst case power in this case. So worst case power is when this is up to 14 volts. So let's start with this. I is equal to 14 volts minus 5 volts divided by a resistor of 200 ohms. And for that, we're going to get, don't tell me, 45 milliamps. Okay, so that's 14 here minus 5 there is 9. 9 volts divided by 200 ohms is 45 milliamps. So now we're going to get I squared R is equal to 0.045 squared times 200. And for that, I got 0.41 watts. So for this, I would not use a ½ watt resistor. It's going to get hot. But if we go up to a 1 watt, they don't make 1.5 watts. I know I usually say 3 to 1. They don't make 1.5 watt resistors that I know of. We could go up to 2 watts, but I think a 1 watt resistor will be okay for this. So we're going to do a 1 watt resistor. Okay. And then the last thing we have to calculate is the power of the Zener diode. So power of the Zener diode. And that's going to be I times V. Okay. So we've already determined that worst case current through here is 45 milliamps. And if the load resistor here is gone, the entire 45 milliamps is going to go through the diode. So we're going to use 45 milliamps times 5 volts equals 0.7, about 0.2. 225 milliwatts. 225 milliwatts. And 225 milliwatts, we could probably okay using a 1 watt Zener diode going 3 to 1. So we could use a 1 watt Zener diode. We could probably get away for a half watt because we're not in this for 10,000 hour reliability. So what we'll do then, we're going to build this circuit here, do a line test, varying the voltage Vs from 8 to 14 in 1 volt increments. And then we'll do a load test with RL starting. We'll probably start at around 1K and then just gradually bring the RL down. And we'd be able to get I out is equal to V out divided by RL. And we're going to graph it on a curve that looks like this. And we're going to see where we find this knee where we've overloaded the supply. So that's what we'll be doing for part 3. Okay, welcome to part 3 of the experiment. We're going to be doing our Zener diode-based voltage regulator. And the first thing I'd like to do is get our IZD min. What's the minimum current it takes to keep our Zener diode at about 5 volts. So we've got it in the curve tracer here. It's in the prongs with the stripe down. We've selected the left module over here. And we're going to gradually turn the voltage up. And we can see that we hit the 0.7 forward bias very quickly. But we got to get to about 5 volts in reverse bias. Right about there. And this is set up for 2 milliamps per division. So if we count down, we're getting really into the good stuff. Right about here is where the line really looks the most vertical. And 2 milliamps per division, so that's 0, that's 2, that's 4. So 5 milliamps for a Zener diode minimum current is a pretty good guess. We're just where the curve here starts to be level. And so our IZD min of 5 milliamps was good. Even if we are off by a little bit, not a big deal. But I want everybody okay with the idea that you want to keep at least this much current through the Zener diode to hold you at 5 volts. And that's the job of our RS. So that looks good. And we can go ahead with our calculations. So I'm going to be careful to turn this all the way down before I take the diode off. Shut off the module selector. The curve tracer has once again faithfully done its job after what, 50 years? This is probably 50 years old. It's amazing how nothing you buy now will last that long, unfortunately. Okay, so we can let that rest. So we have our series resistor. This is a 2 watt resistor and it's ceramic. That is very heavy duty. So, and what I'd like to do is I'd like to go ahead and plug that in here to the binding post so I don't have to worry about forcing it into these little tiny holes on both ends of the board. So let's just move that out of the way and we can see the holes are right there. Okay, and then from there, we're going to go onto the board. Hopefully we can get one end to plug in. There it is, okay. And then we need our Zener diode. This is the Zener diode that we just tested. And this time it goes in with the stripe up, not down. So we're going to put the Zener diode on the board with the stripe up. Top of the diode here, bottom of the diode on this ground bus. Get in there, you. There we go, okay. And then we finally have our load resistor. And for now, we're using our load resistor, which is a 500 ohm resistor. And for that one, we have a 510. Green, brown, brown is 510. And the load resistor is placed directly across the Zener diode. So that's going to go from there also to ground if it'll reach. We'll make it reach. So that is our circuit. And then we have our DC source here. This is going to be ranging from 8 to 14 volts. And then we're going to use this to measure our output voltage. So we just need to connect up on the volt, ohm, and common setting. And the common, let's just plug into the ground here. Very convenient. And for this one, we're just going to need a handy alligator clip and put this on the output. And I'm going to clip onto this big wire because mechanically it's the strongest. So that should be good to go. We're going to turn this on to DC volts. Okay, and let's just do a quick test. Let's gradually bring this voltage up and see if it does level off here at 5 volts, because if it doesn't work, there's no sense taking data on it. So we're going to gradually crank the voltage up, and this should agree with that. Okay, should agree with that. It's off by a little bit, 1.4 and 2.01. That's unusual. Okay, we are going to be getting some IR drop across there. Let's just see if they agree directly. Yes, they do. Okay. All right, that's good. That's fine. So we're just going to gradually turn this up and see if this levels off at 5 volts. So we're up to 8 volts here. And here we're asymptoting it around 5 volts. Here's 10. There's 15 volts, and we're still at about 5 volts. So it looks like it is working. So at this point, we can go ahead and take some data. So let's go a little bit above and beyond. I know we're supposed to go from 8 to 14 volts, but let's start at 5 and see what we get. So what I'll do is I'll dial up a voltage here, and I'll read you this voltage and that voltage, and then you can use them to put together a graph of V in versus V out, and that will be the line test. So paper and pencil ready? We can get started. When we've got 5 volts going in, we've got 3.44 volts coming out. So we really have not gotten to the point where we're regulating yet. There just isn't enough current to wake up the Zener diode. So let's bring this up to 6 volts. At 6 volts coming in, we're about 4.1 volts coming out. You don't really need to get the full 4.5 digits because you're graphing this. 2 significant digits is probably fine. So let's go up to 7 volts. We're about 4.55. We're just at the point now we're starting to regulate. Now, if we wanted sooner regulation, we could have had a lower value of RS. It never hurts to touch RS once in a while, make sure it's not hot. Although this one is built to get very hot. This resistor I may worry about. We'll see how it does. So 7 volts in, 4.54 volts coming out. Now we're going to come up to 8 volts. 8 volts in, 4.77 volts out. There's 9 volts in, 4.88 out. So now we're at 10 volts in, 4.95 out. So we're now getting close to the 5 volts where we're supposed to be. Okay, now 11 volts in, 4.99 volts out. It's leveling off nicely now. 12 volts in, 5.02 out. 13 volts in, 5.04 out. 14 volts in, 5.06 out. It's really hovering nicely at around 5. Let's do a couple of more points just for fun, just because we had nothing else to do. 15 volts in, 5.08 out. And also really curious to see if our load resistor here is going to get upset if we're driving it too high. So hopefully it won't get charged if we burn it up. 16 volts coming in, 5.1 volts coming out. RS is not getting hot. Our diode is not getting hot. It's warm, but it's not hot. And the resistor is fine because it still only has 5 volts across it. So let's do 2 more points. 17 volts coming in, 5.11 volts coming out, and let's stop at 18 volts. 18 volts coming in, 5.12 volts coming out. And we're drawing a current of about 58 milliamps. I think we had calculated at 14 volts, about 45 milliamps. And this is reading about 40 milliamps, but this is with the load in place. Without the load in place, I think we would get 45 milliamps. Well, maybe not. Maybe not. Okay. All right. So that concludes the line test. Let me just reinstate this resistor. Actually, we don't need it for the second part, so I can take it out. So the next part is going to do the load test. Let's again bring this voltage. We're going to set it for 11. We're setting the voltage here just for the middle of the range to do the load test. It's the best representation we can get of what happens at 8 and at 14. If you're doing this in industry, however, you'd probably want to do a complete test at 8 volts and again at 14 volts. If it works over the entire range, it's guaranteed to work everywhere in the middle. So for this, we're now going to use our decade box. This is a very nice box. Inside, it just has 10, 20, 30, 40, 50 resistors and these multi-position switches, and you can dial up in here any resistance value that you need. Now, right now it's set for 0, and that's a little dangerous because anything we connect it to will be shorted out. So let's dial in some token resistors. Let's do 1K of token resistance. And it's confusing. There are 2 terminals on the top that say comparator, 2 terminals on the bottom that say decade. It's the decade that we want. So we're going to plug this into our circuit. And notice it's not polarized because a backwards resistor is still a resistor. And we can go ahead and plug that into our circuit. So the bottom lead here, we're just going to be able to connect to ground. So let's connect that to ground over here on our power supply to keep it out of the way of the circuit. And then we'll just need one more lead to connect up the positive. All right, thank you, sir. So the positive lead here is now going to connect to our output. And again, that can just be plugged in right here where the voltmeter is. So let's plug that in over here once again, just to keep the clutter at our circuit down to a minimum. Okay, so this would be a good idea to just check 5 volts. We're good at 11 volts coming in. That's good. So what we're going to do then is we're going to gradually reduce our resistor value. So let's start with something really high, like 5K. We know that it works well at 500. So with a 5K load, we're at 5.04 volts. So we could write down that point here, and then we're going to gradually drop it down to 4, 3, 2, and 1, and then we'll go down into the hundreds until we see this start to really drop off. So at 5K load, we're at 5.04. If you have to calculate output current, it's just 5 volts divided by 5K is 1 milliamp. We're drawing 1 milliamp for your I out. You do the calculation. At 4K, really unchanged. At 4K, still about the same. At 3K, also really unchanged. It's holding very steady for load resistors in the K. Okay, at 2K, we're starting to see a little bit of a change, 5.037. And then at 1K, 5.022. Again, the voltage now is starting to drop. So now let's go down into the hundreds. I'm going to turn this up to 900 and that to 0. So there's 900 ohms, 5.02, 800 ohms, 5.015. And so what we're hopefully seeing is that the resistor value comes down, the current goes up. And as we saw from the graph, as current goes up, your output voltage gets loaded down and it's going to start to come down. So there's 700 ohms, 5.01, 600 ohms, 5.002, 500 ohms, which is where we did our first round of testing, 4.99, 400 ohms, 4.97, 300 ohms, 4.93, 200 ohms, 4.75. Now we're starting to see some departure. Okay, 4.75. 100 ohms, now we've lost it. 3.43. Okay, but let's still work our way even further. We're not going to burn anything out. These are all 2-watt resistors inside. They're pretty steady. It's pretty sturdy. So let's bring this up to 90 ohms. So there's 90 ohms, 3.37. Okay, 80 ohms, 3.06, 60 ohms, 2.76. We can see we have clearly lost the regulation. We are now overloading our Zener regulator. 600 ohms, 60 ohms, 2.47, 50 ohms, 2.22. And that's why we're happy to have a high-powered resistor in here, because when we're driving this much current, you see that 39 milliamps over here, we don't have to worry about this resistor getting hot or the Zener diode getting hot, and they are both still nice and cool. So 50 ohms, if you want to go further, 40 ohms, now we're really losing it. Now the diode is out of the picture and all we have is a voltage divider. This is R1, this is R2, and this is just going to act like a voltage divider now. The Zener diode is passing no current, it may as well not even be there. You unplug it, no change. So right now we're just testing a voltage divider and you all know what that does. So for your lab report, I'd like to see two graphs, line regulation and load regulation, with a slope on the level part of each one, giving a percent regulation. The flatter they are, the better the quality. The lesson I'd like to take you from this is that if you need a reference source for a signal that's not going to be very heavily loaded, a Zener diode is a nice way to do it. They're available in a variety of voltages, and you can get an easy voltage reference without having to go out and buy a chip. So that's it for part 3 of the experiment. May the force be with you.